All right, welcome. So today we are starting our unit on quadrilaterals. We know that quadrilaterals are basically any four-sided shape or any four-sided polygon, right? So this is sort of an extension of what we were doing with triangles, sort of taking everything to the next step. So we know that with triangles we had a bunch of different classifications, right? We had different types of triangles. So we had our isosceles and our equilateral and our right triangles and all those things. Well, quadrilaterals is the same idea. We have four-sided figures. In general are quadrilaterals. And then from there we have different types of quadrilaterals that we can classify based on the various properties. So the first one that we're going to look at for today is parallelograms. So basically a parallelogram is a four-sided figure, so it's a quadrilateral, where the opposite sides are parallel to each other. So if I'm looking at the picture of this first example right here, I know that the sides on the top and bottom are parallel, and then I know the sides on the left and right are also parallel. So this first table is basically going to take us through some properties that come from that fact, right? So in order for both sides to be parallel to the opposite side, the opposite sides must also be the same length. So not only are the opposite sides parallel, they are also congruent. As far as the angles go, we can use our properties of parallel lines to understand sort of how these angles are supposed to match up. So if we remember from previous lessons that parallel lines have different angle pairs, right? So we know that on the left side, say these two angles here, we're looking at a set of consecutive interior angles, and we know that those are supplementary. Well, if the sides on the left and right are also parallel, then angles J and K are also same side interior angles, which means that those two angles are supplementary as well. So if you notice, two angles on the same side of the parallelogram will always add up to 180 degrees. Therefore, the angles that are in opposite corners are going to have to be congruent so that all the angle pairs add up the way that they are supposed to. So when you look at the values of each angle, the opposite corners are congruent, and then the consecutive corners are supplementary. And then the last piece, if I give you a parallelogram and I give you one corner that's a right angle, in other words, we have one set of perpendicular sides, then using the rules we had above, the other sides also have to be perpendicular in order for the congruence and supplements to work out properly. So if I have a right angle in the top corner, I have to have one in the bottom corner to make those two supplementary. And if I have a right angle at J, I have to have a right angle at L because those two are supposed to be congruent. So when we're looking at examples, basically the first thing we're going to need to be able to do is fill in values and sort of identify the different parts based on what they've given us. So if we know that measure of angle A is 55, and we know that the length of AB is 2.5, and the length of BC is 1, we should now be able to figure out the size of each remaining side and angle. Right, so it's asking us to find the length of DC. So opposite sides are congruent, therefore DC must be 2.5. It says to find the measure of angle B. Well, I know that measures A and B should be supplementary. So if I have 55 degrees at A, I need 125 degrees at angle B. And then finally, I know that opposite corners have the same measure, so angles A and C should be congruent, so I should have 55 degrees on angle C. So the next thing we're going to look at are the diagonals. Right, so a diagonal basically means it is a segment that connects the opposite corners, thus generally making diagonal lines. So if you notice, when I trace out my triangle, so let's say I connect A and C and make a triangle, since the opposite sides have to be congruent, and AC is in both that red and green triangle, it means that my triangles are congruent. Well, the same thing is true if I connect B and D, right? The left triangle and right triangle are congruent. So what's going to end up happening is that the diagonals bisect each other, creating two pairs of smaller congruent triangles. So we can use that knowledge to solve for these variables. So combining what we just pointed out with what we did in the first example, we should be able to set up equations to solve for all the missing parts. So I have my x over here, and I know that the opposite sides are supposed to be congruent, so that means 5x should equal 27, which means x should equal 5.4. For y, we just said that the diagonals bisect each other, right? So if I draw my diagonal from Q to S, it's going to cut T to R in half, which tells me that the length from T to P is the same as the length from P to R. And so then we solve it out. We should get that y equals 9. Finally, for z, right, we said that all the opposite sides are parallel. Right, so this is going to be parallel to this. I notice that I don't have an angle for z, right? But I know that there's a 33-degree angle up here and a 95-degree angle down here. So if we remember with parallel lines and transversals, the alternate interior angles are congruent. So that's going to tell me that 3z should be equal to 33. So z must be 11. All right, so the last thing we're going to look at is applying those properties to coordinates. So if we want to find the point of intersection of the two diagonals, right, we're going to need to plot the 4 points. F here. Here's G. And then there we go. So if I connect those lines, I should get a nice little parallelogram. Let's do that. All right, there we go. We need to find where the diagonals intersect. So connect your opposite corners. We should be able to see it on the picture, right? It looks like it's about the origin. More or less right here. but our picture might be slightly off, so let's make sure we know how to do it for real. So if we label our points, right, this was F over here, this was G over here, this was H, and then we had J. And so we said if we draw the diagonals, they will always intersect in such a way that they're bisecting each other. Right? So if they intersect or they bisect, they meet in the exact middle of each line, which is your midpoint. Right? So I should be able to take those coordinates, find the midpoint of one of my diagonals, and it should give me the point of intersection. So let's see. To draw the diagonal, I need to connect F to H. And we remember that our midpoint, we're just going to add the coordinates, divide by 2, because again, midpoint is the same as taking an average. So if I take -2 plus 2, divide it in half, that'll give me the x. If I take 4 minus 3, divide it in half, that'll give me my y. And so for the x, we get 0. For the y, we get a half. And so if you look at that picture, look at where they actually cross. If all my lines had been perfectly straight, we can see that it actually does hit a little bit higher than the origin, right? It's not exactly at 0, 0. If we're not convinced, if we want to do one more calculation just to be sure, right, the other diagonal went from G to J. So I should be able to get the exact same thing here by finding that point of intersection. So I'm going to take 3 minus 3 divided in half. I'm going to take 5 minus 4 divided in half. And so once again, we get 0 and 1/2. So not only have we confirmed our point, we've also really confirmed the theory that we had in the first place, which was that the point of intersection is the midpoint of both lines. All right, that is all we have for today. So I will see you guys next time.